Okay, this problem is a little bit different than previous problems because here we have a case where we have an initially charged capacitor. As you can see, the 2 microfarad capacitor has an initial charge of 10 volts. And when the switch closes in this circuit, current will flow from the capacitor to the 2-volt source, right? Because as we know, current's going to flow from the higher electric potential, the higher voltage, to the lower electric potential, the lower voltage. So this is a discharging case because anytime current leaves the higher voltage end of a capacitor, and here is the higher voltage end indicated with the plus polarity symbol, well, this means that the capacitor is giving up energy to the circuit, okay? That it's supplying power since the current is flowing out of the higher voltage end. So you see this problem is different than any of the previous problems because here you have a discharging case where in the discharge path there's a source along with the resistor. The previous video we had a discharge case where there was just resistance in the discharge path, and in that case all the stored energy was depleted and dissipated as heat, and the final voltage, the steady state voltage for the discharge capacitor, was 0 volts. But you see, you're going to see we get something different here because there's a voltage source in the discharge path. So down below, these are the set of curves for the discharge case. So this is what we have. We have a decaying exponential for the voltage for the capacitor and also a decaying current. This is the charging case, as you know, or as we've seen. And in this case, those two curves do not apply. Okay? So we're going to start off finding where these curves start using the t equal to 0 plus analysis. So here's our t equal to 0 plus circuit. We replace the initially charged capacitor of 10 volts with a voltage source at 10 volts. And now if we were to find the voltage across that 10 volt source, well, that would be the voltage across the capacitor at t equals 0 plus. And then if we find the current for the 10 volt source, well, that's the current for the capacitor at t equals 0 plus. Okay, so right here, the voltage across a 10 volt source, of course, is 10 volts. So that's easy. And now we look at, well, how do we get this current? Well, we could just do a KVL equation across this path here. We'd have 10 minus 2. See this 8 volts, the 10 minus 2, that's the voltage that's across these two resistors in series, right? Because as I do a KVL, I go up 10 volts here, I go down 2 volts here, so I must go down the remainder, the 8 volts, across the two resistors in series. So to get the current, it would just be that 8 volts divided by 25K, the value of those two resistors in series. So that works out to 8 over 25K, which is a little less than 1/3 of a milliamp. It's 0.32 milliamps. Okay, so if we go back to our curves, we have that this voltage here is 10 volts, and this current is 0.32 milliamps. All right? Okay, well now let's think about what the steady state values would be. Again, if this voltage source was not present, this 2 volt voltage source, say all we had was this 10K in the discharge path, well then this voltage for the capacitor would go to 0, just like it did in the previous problem, okay, on the previous video. But you see, by having this 2 volt source in the discharge path, this current flowing out of the higher ends of our capacitor, okay, well, it will flow as long as the voltage across the capacitor is greater than this 2 volts. See, once the voltage across the capacitor gets to 2 volts, current is going to cease to flow. See, so when the capacitor voltage is 10 volts and 9 volts, 8 volts, and so on, all the way along this part of the curve, its voltage is greater than the 2 volts and current's going to flow. But then once the voltage across the capacitor equals this source voltage, the current ceases to flow. See, this now becomes 0. See, once this becomes 2 volts, IC will become 0. And once the capacitor current becomes 0, the capacitor is finished discharging. So you see, that's what's different from the previous discharge problem, is that anytime you have a discharging capacitor where in the discharge path there's a voltage source, the steady state voltage, okay, the voltage that the capacitor discharges to, will equal that source voltage that's in the discharge path. Okay, so you see this exponential, decaying exponential, it decays from 10 volts to 2 volts. Okay, it doesn't go to 0 volts. The capacitor current will still reach 0. Okay, so this capacitor current will still reach 0. That's a better representation here than what I had previously. Okay, so this will still go to 0 amps at 5 time constants. Okay, so that's how you get the steady state for this type of situation. Now, the one last thing to do here is to find the time constant. So tau will just be Req times the capacitance. So we got 25K, and that's going to be multiplied times, what was our capacitor value in this problem? It was 2 microfarads. Double check here. Yeah, 2 microfarads. Actually, did I write that down? I might have forgot to write that down on the... Oh, no, I didn't. Right there, 2 microfarads. Alright, so that's going to give us a tau of 50 milliseconds. And then 5 taus is just 250 milliseconds, which is a quarter of a second. Right, so 5 taus would just be a quarter of a second. Alright, so the time from t equal to 0 out to steady state quarter of a second. Okay, so that completes this video, and we'll have just a couple more videos with some additional analysis of these first order circuits.